Alright, so this is part 2 working on the classwork for the Chapter 10 and 11 review. So the first question we're going to start with is number 19. This problem, the question is asking for moles, and it gives us molecules of H2SO4. So with these conversion problems, we start with what the problem gives us. So in this case, it's 1.5 times 10 to the 23rd molecules of H2SO4. We set up our conversion factor, and then we set it equal to. Now the problem's asking for moles, so we're going to put moles over here, MOL. Now, because we want molecules to disappear, because we have molecules right there, we want that to disappear, or to cancel out, so we're going to put molecules down here. And then the unit that we want to be left with are moles, so we put moles up here. Now, we need to remember that according to Avogadro's number, 1 mole of either atoms or particles equals Avogadro's number, which is 6.02. So I'm just going to leave it at 6 times 10 to the 23rd power. So that's the problem set up. Now we just have to do the math. So we take the problem. Remember, this part right here, even though it's not written, is over 1. So we're going to write this as 1.5 times 10 to the 23rd. Now it's being multiplied by 1, so we could just leave it as that. And then it's going to be divided by 6 times 10 to the 23rd. Now, according to your algebra rules, 10 to the 23rd divided by 10 to the 23rd, those cancel off with each other. So this is written as 1.5 divided by 6. Now, hopefully you can do this by hand, or at the very least by a calculator. 1.5 divided by 6 equals 0.25 moles, and that is your final answer. Okay, next we have problem number 20. Similar problem. This time it gives us 51 grams of NH3, and it asks for moles. So we start with what we're given, which is 51 grams of NH3. Okay, we set up our conversion factor. We're going to put grams on bottom because that's what we want to get rid of. And the problem is asking for moles, so we're going to put moles on top. Okay, and remember, the reason why we do this is we want grams to cancel off, so we're left with moles on both sides. Now, to figure out how many moles or how many grams are in 1 mole, we have to use the periodic table. So if you use the periodic table, we get that nitrogen is equal to 14 grams. Hydrogen is equal to 1 gram, but remember we have 3 of them, so we have to multiply that by 3. So NH3 is equal to 17 grams. So now what we do is we just set up the math. We have 51 times 1 is 51, divided by 17, that equals 3. So our answer here is 3 moles. All right, next we have question number 21. And again, you'll start to notice that these conversion factors are all very similar to each other. You just have to identify what you're starting with and then identify what the question is asking. So for this question, it gives us 3.01 times 10 to the 22 molecules of N2I6. Next, we set up our conversion factor. And finally, we write down the units that it's asking for, which are moles. Okay, or we could just leave that as MOL. Okay, molecules we want to put on bottom because we want them to cancel out. And moles we put on top because that's what we're wanting. So again, to compare moles to molecules, we use Avogadro's number, which says that 1 mole is equal to 6.02 times 10 to the 23rd molecules. So now we have our problem written out. We just have to do the math. Okay. We notice here that we can't just do simple division because we have this times 10 to the 22. So we have to address that first. If you notice, we have 10 to the 22nd power over here, but in this problem we have 10 to the 23rd power. So the easiest way to solve this problem is to make them both at 10 to the 23rd power. So I'm going to start by writing this 3.01 times 10 to the 22nd. Now I just said I want to make them both to the 23rd, so I want to change this exponent and make it a 23. Now, with scientific notation, if your exponent gets bigger, then that means that this number out front needs to get smaller. The way you make it smaller is you move the decimal to the left to make it smaller. So by changing your exponent to 10 to the 23rd, you make your number out front 0.301 as opposed to 3.01. So now we have 0.301 times 10 to the 23rd, and now we can divide it by 6.02 times 10 to the 23rd. Okay, 10 to the 23rds, those cancel off. So now we basically have 0.301 divided by 6.02, and this gives us a final answer of 0.05 moles. So we come up here, put our final answer up here, 0.05, and that is our final answer for this problem. Number 22, we have 3.5 moles of oxygen, and it's asking for how much space. In other words, space is just simply a measure of volume, and the units we're looking for with volume are liters. So now we write down what we're given, which the problem gives us 3.5 moles of oxygen. Then we set up our conversion factor, and we are converting it to space, or in other words, liters. So here we put moles on bottom, liters go on top, and we know that 1 mole is equal to 22.4 liters. Now it's important that the only time this applies is that if we are 1, talking about a gas, and 2, if that gas is at STP, which is standard temperature and pressure. According to this equation, it is a gas and it is at STP, so we can just simply do the math, and when we do the math, our final answer is 78.4 liters, and that is the final answer. Okay, next problem. Again, we are given 5 liters of a gas at STP, and it's asking for the mass. Now, the first thing we're going to do is we're going to convert from liters. We have no way of directly converting from liters to grams because mass is measured in grams. Okay, we can't do that direct conversion. Instead, we have to first convert it into moles, okay, and then once we've converted it to moles, then we can convert it into grams. So this is actually a two-step problem. So there are 2 steps to solving this problem. Now, I'm going to show you how to do this all in one step without doing this as 2 problems. So the first step is we write down what we're given, 5 liters. Okay, so 5 liters of gas, and now we set up our first conversion problem. Now remember, I said earlier that our first step was to convert it to moles. So in order to convert it to moles, I write moles up here, but I have liters over here, so I need to put liters on bottom. That's my first conversion factor. So now I know that 1 mole of a gas at STP is equal to 22.4 liters. So that conversion factor right there will convert me into moles. But the problem, remember, is asking for mass, so I need to do a second conversion problem that is going to allow me to convert from moles into grams. Now again, I want my moles to be able to cancel out. So in order to get them to cancel, I write moles on bottom, and then the number or the unit that I want left over is grams, and so that's going to be my final answer in grams. Now to get your conversion factor right here, we need to use a periodic table and know that 1 mole of chlorine gas, so first of all, chlorine gas is equal to 35.5. Sorry, that's a chlorine atom. 1 chlorine atom is equal to 35.5 grams. So 1 mole of chlorine atoms is 35.5 grams. So if we're talking about chlorine gas, which is Cl2, that's going to be equal to 71 grams. So then we plug our 71 grams up here, and now I do the math. This will be 5 times 71. So once you get that, then you divide it by 22.4, and then your final answer will be 15.8 grams. And that's your final answer. Okay, Next question, number 24. Problem gives us 0.25 moles of argon gas at STP, and it's asking for molecules. So we just simply have to go a single conversion from moles to molecules. So we write 0.25 moles, that's what we're starting with, set up our conversion factor. We're wanting to convert this into molecules. So we put molecules on top, and we put moles on bottom. And again, going back to Avogadro's number, we know that 1 mole is equal to 6. I'm just going to leave it at 6 instead of 6.02 times 10 to the 23rd molecules. Okay, we have the problem set up. Now we just have to do the math. We take 0.25 and we're multiplying it by 6 times 10 to the 23rd. So basically we can take this and solve this part of the problem first. So 0.25 times 6 is basically 6 divided by 4, which would be 1.5. And then we bring down this part of the problem to give us 1.5 times 10 to the 23rd. So our final answer would be 1.5 times 10 to the 23rd molecules. And that's our final answer. Next problem we'll be doing is number 25, part C. Now, although on the left side of the equation we have this NH4 in parentheses, this right here is not the same because this has a 3 down below. This right here is NH3, this right here is NH4, so we cannot leave NH4 in parentheses and do it in parentheses with parentheses around NH3. Instead, we have to break these up by atoms. So we rewrite our atoms in HCO, keep the same sequence on the right, in HCO, do our count. On the left side, we have 1 nitrogen here, but there's a 2 right here, so that 1 gets multiplied by 2. So total, we have 2 nitrogens on the left. Same thing for the hydrogens. Even though we have 4 there, it gets multiplied by this 2. So total, we have 8 hydrogens on the left. Carbons, we have 1. Oxygens, we have 3. On the right side of the equation, we have 1 nitrogen. We have 3 plus 2 hydrogens, so we have 5 hydrogens. Carbons, we have 1. And oxygens, we have 3. So simply just start taking these atoms one by one and try to balance it. First thing we should try to do is the nitrogens. So we have 2 on this side, on the left side, only 1 on the right. So we're going to try putting a 2 out front here. See what that does. That updates our nitrogens to 2, and that updates our hydrogens to 6 here, plus 2 over here, for a total of 8 hydrogens on the right. And now, just by changing that one substance, our equation is now balanced. 2 on each side of the nitrogens. Hydrogens have 8 on each side. Carbons have 1 on each side. Oxygens have 3. This equation is balanced. Alright, last question we're going to do here is G. So again, we need to start by separating our reactants and products and start listing atoms. We have carbon, hydrogen, and oxygen on the left. We have carbon, hydrogen, oxygen on the right. Set those equal, and now we're going to start coming up with our list of atoms. We have 2 carbons on the left, 6 hydrogens on the left, 2 oxygens on the right, on the left. On the right hand side we have 1 carbon, we have 2 hydrogens, and we have 3 oxygens, and those oxygens are in 2 spots. So 1 right here, 2 right here. Now, just a little tip. Because I have this oxygen right here by itself, and because oxygen appears in 2 spots on the right side, I'm going to save oxygen for last. That's going to be the very last atom that I try to balance. So the first atom I'm going to balance are the carbons. I have 2 on the left, 1 on the right, so simply just put a 2 here. That balances the carbons. I now have 2 carbons. Oxygens, I now have 4 here, because that 2 gets multiplied by that 2. and then I have one oxygen over here. So oxygens total are 5 on the right side. Next, I go down to the hydrogens. Hydrogens, I have 6 on the left side, 2 on the right side. I want to put a 3 right here so that changes my hydrogens to 6. When I do that, I now have, 6 hydrogens on the right side plus oxygens. I have 4 oxygens here, and now I have 3 oxygens here for a total of 7 oxygens. Now, at this point, I have 2 oxygens on the left and 7 oxygens on the right side of the arrow. Now, I need to figure out some number I can put out front of the oxygens so that when they get multiplied by it, it's going to equal 7. What number is that? Just simply go 7 divided by 2 equals 3.5. So that means I'm going to put a 3.5 right here. However, when we put a 3.5 out front, and sorry, I covered up the oxygen, we cannot leave it as a decimal form. So the best way to get rid of that 3.5 is to multiply every coefficient by 2. So when we multiply the first coefficient by 2, we change it from a 1. The 1 disappears and it becomes a 2. Next, we get rid of the 3.5. We multiply it by 2. 3.5 times 2 gives us 7. Okay, over here we get rid of this 2. We multiply it by 2. 2 times 2 equals 4. And our last one, take the 3, multiply it by 2. 3 times 2 equals 6. And so now our final coefficients are 2, 7, 4, 6. If you double check our atoms, we now have 2 carbons on each side. Actually, we have 4 carbons on each side. We now have 12 hydrogens on each side. And last, we have 14 oxygens on each side. So now our equation is balanced.